This statement cannot be proved. Is that sentence true, or is it false? If the statement is false, it means it can be proved. But if a false statement is provable, the entire logic of mathematics collapses into contradiction. If the statement is true, it genuinely cannot be proved. This creates a reality where mathematics contains absolute truths that remain forever beyond the reach of a formal proof. Mathematics is trapped. Either it is inconsistent, proving things that aren't true, or it is incomplete, unable to reach the very truths it contains. To understand how this realization broke the mathematical world, we have to look back to the year 1900 at the International Congress of Mathematicians in Paris. David Hilbert, the era's most influential mathematician, proposed a vision to solve this once and for all. He wanted to build an unshakable foundation for all of logic. Hilbert's program required two things: completeness, meaning every true statement could be proven, and consistency, meaning the system would never produce a contradiction. For 30 years, the world's sharpest minds pursued this dream. Bertrand Russell and Alfred North Whitehead spent a decade writing the Principia Mathematica, a work so dense it took them over 300 pages of logic just to prove that 1 + 1 = 2. They believed the finish line was in sight. They were unaware that a 25-year-old outsider in Vienna had already discovered why their goal was mathematically impossible to reach. Gödel's starting point was the liar's paradox. This statement is false. For over 2,000 years, this was treated as a philosophical curiosity, a loop of words with no impact on the rigid world of numbers. Gödel's breakthrough was finding a way to translate this linguistic loop into the formal language of a mathematical proof. He invented Gödel Numbering, where every logic symbol, equal signs, variables, operators, is assigned a unique code. By combining these, entire proofs convert into massive, unique numbers. A proof becomes a sequence of numerical properties. This creates a bridge. Because mathematics is the study of numbers, and every logical statement is now a number, the system can perform arithmetic on its own structure. Checking if a statement is provable becomes a simple matter of calculating if one number is divisible by another. Gödel used this bridge to construct statement G, a valid numerical equation that translates to: the number representing this statement does not have a number representing its proof. Or, more simply, I am not provable. The first incompleteness theorem proves there are always true statements its rules cannot reach. The second theorem, no system can prove its own consistency. It is logically equivalent to a ruler trying to measure its own physical length, or a scale trying to weigh itself. These systems fail because they lack an external point of reference. Mathematical logic hits the same wall. It cannot verify its own foundation. Hilbert's 30-year quest for a perfect, self-contained system of mathematics was over. These limits define modern computer science. Alan Turing adapted Gödel's work, proved the halting problem, the fact that there is no general algorithm that can predict if every program will eventually stop or run forever. In artificial intelligence, the theorem suggests that any system built on formal logic will always encounter questions it cannot answer and truths it cannot verify. This has led philosophers like Roger Penrose to argue that human consciousness must be more than a biological machine, because humans can recognize the truth of a Gödelian statement that a computer is strictly forbidden from proving. Gödel's work established a mathematical boundary on how much any system can ever comprehend about its own nature. Gödel spent his final years at the Institute for Advanced Study in Princeton, where he was often seen walking the grounds with his closest friend, Albert Einstein. Einstein famously remarked that his own work at the Institute had lost its spark, and that he only went to his office for the privilege of walking home with Gödel. But the mind that mapped the limits of logic succumbed to its own internal pressures. Gödel developed a severe, irrational paranoia that his food was being poisoned by hidden enemies. He eventually refused to eat anything not prepared by his wife. When she was hospitalized for several months, he stopped eating entirely. Kurt Gödel died of starvation in 1978, weighing only 65 pounds. We are left with the profound truth his math revealed. The universe is too vast to be trapped within a set of rigid rules. Mathematics' greatest achievement was finding the exact location of its own shadow.